So we'll finish the icy moons. We're going to look we'll look at Neptune, and we'll look at Uranus for just a minute. We'll talk about Pluto. And then we're going to do the asteroids, and we'll talk about asteroid mining, and maybe most importantly, we'll talk about planetary defense, because this has become an increasingly real threat, which is interesting that people weren't too worried about it until the 90s. But it became a real big problem. A couple of things happened, actually, that made asteroids a big concern with us. One, we saw a huge comet break up and crash into Jupiter. I don't know, I think that was in 94. Don't quote me on that. It was in the 90s. And then about a decade later, this Chicxulub hypothesis was essentially solidified. And I didn't realize that was so recently, but this idea that the dinosaurs were wiped out by an asteroid is actually a relatively recent consensus. And so these two things put together have really kicked off a lot of funding and legislation aimed at keeping track of all of our near-Earth objects. Because it turns out we're actually getting hit all the time with these things, and some of them are quite large, and I want to give you guys a sense for that later and look at the actual impact power that we're getting out of some of these collisions. But we're doing pretty good. We're actually able to track most of these things now, and there's a number of missions. We talked already about the DART mission, so I'm not going to do that again, but there's a number of remediation strategies, which are all pretty interesting and cool for how to deal with the near-Earth objects that might be on a collision path. And there's they're very different strategies that are everywhere from diverting them to blowing them up to putting solar sails around them. A lot of really interesting strategies, so we'll get to that hopefully later today. But first, let's finish up our moons. So we made it through Saturn last time. Moving outward, we get to Uranus, which is one of my favorite planets. Uranus and Neptune are quite interesting because in terms of planetary science, they're starting to really, they're real paradigm shifters, these types of planets, in terms of understanding the origin of our own rocky bodies and so forth. I had the pleasure of speaking with another guy over at Caltech, and I introduced you to Konstantin Batygin, who works on these also at Caltech, and he plays in a band actually with another scientist who's over there, and I met with this gentleman. His name is Petagura, over last week, and he's working on that interesting problem that I talked to you guys about with the radius gap, where you find these mini Neptunes that are very close in size to super Earths, and there's this interesting space where you don't see planets of a particular size, and they're trying to explain why that is. And if these super Earths are in some sense a moment on the evolutionary timescale between Neptunes and something that looks like Earth, which is really interesting. This science is changing so fast. I think it's really exciting. It's also one of those places in science that planetary science doesn't necessarily impact policy on Earth so much, and so the scientists are much more experimental with their ideas. They're much more willing to entertain new ideas very quickly. A lot of the paradigms in terms of biotech and so forth are very rigid because, of course, our health policy depends on it and so forth, but planetary science is really on the move, which is super cool. And so, it always struck me when I was your age and so forth, how strange it is that these that something like the Earth, which is very, is it the most dense? It's one of the most dense objects in the solar system. Why isn't it inside of the sun? How did this happen? How did something accrete so dense in orbit around something else? It's very strange. And so the idea that it could be there's this evolutionary process is really exciting to me. Anyways, so Uranus. Uranus has a number of moons. It's actually got 27 known moons. And we divide them into 3 groups. There's 13 inner moons, 5 of these major moons, which you can see here. And then there's some irregular moons. So the inner and the major moons all rotate in the same direction as the planet. They all orbit, which we call prograde. And the irregulars are going retrograde, which is very strange. They go the wrong way. And of course, this makes us think of, this almost necessitates that they weren't formed in place, that they were scooped up later somehow. And I think these capture events are also one of the most exciting windows into possibilities of massive cataclysmic changes that have happened in the past in the solar system. The more that we learn about how solar systems are formed, the more obvious it becomes that things sometimes change a lot very quickly, which is very strange, and I think maybe perhaps a little disconcerting as well. I asked Padagura when we were doing this podcast with him about how stable the orbits were, and he basically said that there's no way of knowing. Like these balances are so tight that our forward velocity is perfectly matched to our gravitational pull towards the sun. The tiniest changes in any single body is going to ripple through the solar system and affect any of the other bodies. And when we'll talk about Pluto later today. And Pluto has a very chaotic wobble to it. And so, it's not understood exactly where Pluto will be in a million years or something like that. And there's really no way of being able to predict that. There's too many factors. When you think about something as small as Pluto, but also as large as Pluto, not being particularly unique. So you all are aware that Pluto lost its planet status a few years ago. And that's because there's a lot of objects out there by Pluto that are about the same size. And we're just starting to learn all about those within the last, 10, 20 years. So again, minor changes in one orbit can affect everybody. There's some interesting discussion about that. I came across a really interesting piece of work this last week by a historian of astronomy who was looking at some ancient Vedic records of the orbits of the main bodies that you can see, Venus and Mars. And there's this isolated book that actually predates the Sumerian records, because most of our records of historical planetary position come from the Sumerians, which is like the Neo-Babylonian period, which was like 800 BC. Before that, we don't really have much of a record except from the Indian subcontinent and the Vedic astronomers. And they have slightly different orbits for a lot of these bodies. But what's really interesting is that all of these orbits seem to be a little bit longer back then, like by about 4 days. And it seemed to correspond to all of the planets. They were all in such a slightly different orbit that they corresponded with one another perfectly. And so it made it a sort of tantalizing piece of evidence that there may have been some change in the past. But, it's a 1,000-year-old piece of writing, and it's all alone. So we don't really know what happened there. But these things can change, which is interesting. And we would be wise to study it and understand it better. So the moons of Uranus seem to have similar origins and properties to the rings of Uranus, which we didn't too much talk about, but Uranus is strange. It's tipped on its side, which is very bizarre. The rings have a host of anomalies. It's thought that they must be continually regenerating themselves, and it's thought that they're essentially comprised of bits of detritus and wreckage from the collision of moons, which must be happening all the time, actually, in order to sustain them. Otherwise, they would have disappeared a long time ago. And so there's something of a a wreck out there around Uranus, where all of these bodies are smashing into each other and continually being renewed. We'll talk about. We're not going to go too deep into Uranus's moons in general. The largest of these, which you can see up here, is called Titania, not to be mistaken with Titan. It's actually the 8th largest moon in the entire solar system, but it's quite a bit smaller. It's about a 1/12 the mass of our own moon. And yeah, it's interesting. So these irregular moons too are strongly inclined, and the irregular ones orbit the wrong way, which is very strange. Let's, in the interest of time, let's check out Neptune. Neptune has a moon that's really interesting. I want to spend a little bit of time on, which is called Triton, which you can see. This is Neptune, and then Triton's down there below it, which this picture was actually taken in 1989 by Voyager 2, which is kind of cool. So Neptune has 14 moons, a bit fewer than Uranus. And of course, this Triton one is the largest. And they actually discovered this. A gentleman named William Lassell discovered this in 1846, a couple of weeks after Neptune itself was discovered. What can we say about Triton? So Triton's kind of strange. So among all of the different planetary mass moons or bodies, it orbits retrograde. So it's inclined relative to Neptune's own equator, and it goes the wrong way. So it's very strange because it's a pretty big body that may have been captured by, must have been captured almost certainly. And this is another thing that I was talking to this guy at Caltech about was, what are the odds that some of our own planets even didn't actually form here in our solar system, but were scooped up by from another solar system, because of course Jupiter and really Saturn to some extent, they're very close to brown dwarfs, which are these failed stars. They form in the same way that a star forms, except they don't have enough mass to ignite and glow as a true star. And they're very similar to these wandering rogue planets too. And Pedagora said something like, well, it's possible, but these things are cruising through outer space. Excuse me. They're cruising so fast that if you can imagine one out there moving through space, it's very unlikely that it's going to hit another solar system at just the right angle to be scooped up and dragged into orbit. But it's not out of the question either, right? And it's very difficult for humans to conceive of rare events as being possible because we have this bias where, of course, everything that exists seems to be likely to exist, but in reality, we don't see a lot of obviously we don't see any other planets that look exactly like Earth with civilizations and so forth. So we know that there's some very rare selection going on with a lot of these processes. It may be the case that solar systems are forming all over the place, but none of them are stable enough to be sustained long enough for us to even get a picture of them at all. And so it's not clear exactly how important it is that rare things may or may not occur. So it's an interesting idea that's still hanging out there. So you can see Triton there next to our own moon. It's much less dense than our own moon, though it's not that much smaller. Now, what's interesting about Triton is it has about almost all of the mass of Neptune's moons are contained within Triton. It's a very big body considering the rest of them. It's actually the 16th largest object in our solar system, just a little bit bigger than Pluto and Eris, which is another one of those trans-Neptune objects. And like I said, it's in retrograde, which is interesting, so perhaps scooped up. And when we get to Pluto, we'll talk about where did Pluto come from, and there's thoughts that Pluto may have also started out, it may have spent some time in the more or less recent past as a moon of one of these larger gas planets. So moon trading seems to be a thing that happens in the deep past. So what else can we say? Triton also is the largest moon of any gas giant relative to its host planet in terms of diameter. But Titan is actually bigger in terms of mass relative to Saturn. So there it is. It's actually kind of a beautiful planet. Since it's tidally locked, one side's very different than the other. And as a result of that, we've only checked out about half of its surface. Seems like the surface has this transparent layer of frozen nitrogen, which is really interesting. Of course, our atmosphere is very much nitrogen, and we can use nitrogen as a rocket fuel source too, so there's a lot of interest in using it as a waypoint in our future missions. The ice has a lot of water content too, which is also quite useful. Frozen carbon dioxide as well, about 35% water ice, which is interesting. There's traces of methane, carbon monoxide. And then overall, in terms of the density, we think that Triton has about 30 to 45% water ice in its body, which makes it quite useful. It has this kind of reddish color, which we've talked about before in terms of indicating the presence of organic molecules, which may or may not reflect some biotic past. It's difficult to discern without going there. But this is the result of UV radiation interacting with the methane ice, and it creates these tholins. People think that Triton is differentiated. They see a lot of melting on the surface, and this sort of like Earth gives us this idea that there's a solid core, a mantle, and a crust. But of course, it doesn't seem to be sustained at the moment because there's no magnetic field. But there must have been something in the past because there's quite a bit of recent-looking surface geoactivity. And if if we do find some sort of liquid water that exists in the subsurface, it may be habitable for life, but we won't know until we check it out. It's got a little bit of an atmosphere. I know we talked about, you mentioned that Titan had kind of the most pronounced atmosphere, right? All these guys have, not all of them, but many of them have a very thin, weak atmosphere. Even technically our own moon has a thin little atmosphere, but it's kind of a joke, right? We're talking about like parts per billion gas molecules. Of course, the gravity is really weak on these things. This being 1/12 the mass of the moon, it's just not going to hold on to anything very well. But its atmosphere does seem to be nitrogenous. There's a bit of carbon monoxide and some methane. And it's generally thought that atmosphere results from the evaporation of the ice surface. Though it looks like there's a little bit of weather going on there, which is quite interesting. There's some streaks on the surface, which are thought to be left over from geyser plumes, and then maybe driven by some sort of seasonal wind, depending on how it tilts towards the sun. Voyager 2 found a few of these eruptions, a few geyser-like eruptions, which were thought to be trapped nitrogen gas bubbling out of the surface, which is kind of interesting. So, just like Earth and Io and Europa and Enceladus, it's one of the few bodies where we see these active geysers going on, which is, I think, quite exciting in terms of being able to penetrate the surface and learn about the interior. And each one of these geyser eruptions on Triton lasts maybe a year, where it's sublimating. Sublimation's when you go from a liquid to a gas very quickly. It boils off, right? Very quickly. And it's something like 3.5 billion cubic feet of nitrogen ice over a year, which is a lot. Another thing that's kind of interesting is that since we first went there with Voyager 2, there have been some long-range observations from Earth that have shown that the temperature has decreased over about a decade by about 5%. So the thing's cooling really rapidly, which is quite fascinating. So maybe the geological history was more recent than we think. Maybe some of these processes that we're churning it up are rapidly ending. That would be a cool chance to study the evolution of a body. The surface is maybe slightly familiar to some of these other icy moons. It's got this, what they call a cantaloupe terrain. Not very many craters, but it has these little pockets, which, are thought, there's a few ideas about that. One of them is that the less dense material rises up through the denser material as there's these periodic melting phases, and you get these little pock marks. And this process is called diapurism. Other people think that maybe there was collapses or flooding due to these cryovolcanism events that may have happened in the past, which gives it this kind of unique puckered surface. There's some thoughts of being able to go back there. There was a number of proposals back in the 2010s, but nothing really made it beyond the proposal phase. One of the more interesting proposals was this thing called the Triton Hopper, which was going to go and mine nitrogen ice from the surface and then use it, like I said, as a propellant to fly around or skip across different parts of the surface and dig down. But these are all just concept missions. Nothing's actually really planned at the moment. There's another concept that's live right now that would potentially launch in 2033, but it wouldn't get there until 2050-ish. So we'll see. Okay, Pluto. One of the, almost everything that we know about Pluto came from the New Horizons spacecraft, which got out there in 2015 and is currently going into the depths of the solar system right now. So we have some beautiful pictures of it. We've learned a lot. It actually looks not too much different than our previous planet. It's also got these reddish patches, which indicate some organic material. Pluto is actually the 10th most massive object relative to the sun, but it's not that much bigger than a number of the other bodies that are out there, And so Pluto's another one of these trans-Neptune objects. It's a whole class of bodies for which we're aware of hundreds of them at this point, which orbit just beyond the gas giants in this region we call the Kuiper Belt. We'll talk about the asteroid belt later, which is a bit more interior, and which is a little unfortunate that we have to go back into the interior before we finish this journey. But I think it makes sense to do all of the big rounded moon-like bodies first. So Pluto and these others, we call them dwarf planets at the moment, which is a bit arbitrary in terms of threshold. I think people just wanted to separate out the main planets from the rest of these somehow. But in all honesty, even an asteroid is essentially a dwarf planet, which is quite fascinating. Anything that's smaller in orbit, if it orbits the sun, it's a planet, right? So what do you call these things that are a bit smaller? Well, they're dwarfs. Pluto was actually named by an 11-year-old schoolgirl, which is quite interesting. Her dad was a librarian at Oxford who was friends with an astronomer at the time, a professor there named Herbert Turner. And she proposed the name from classical mythology. Maybe some of you will know more about this than me, but Pluto was the Greek the Roman god of the underworld. So sticking with tradition. What else can we say? So Pluto, compared to our own moon, I don't have a picture for you, I'm sorry, is actually only about a sixth of the mass. It's about a third of the size by volume, so it's a pretty tiny little thing. Now its orbit is kind of strange too. It's a bit off kilter, and the inclination seems to be a bit chaotic. The thing orbits about anywhere from 30 to 49 astronomical units, so the distance we are to the sun away from the sun, which is quite a bit out there, and that's quite a range. So there's quite a bit of eccentricity to that ellipse. And at some point in its orbit, it actually comes closer than Neptune to the sun. But it's thought that because it's in this really stable 3-2 resonance with Neptune, it's a musical fifth, by the way, it's stable, right? So Neptune will always pull it out of the way before it can crash into it, hopefully. So one thing that's interesting about that is that the inclination and eccentricity, the tilt and the plane of that seems to be a bit chaotic. So while the orbit seems to be steering clear of Neptune, there's the chance that it could actually come into contact with other things that might be in the way. And so it makes its long-term prediction, like I said earlier, very, very unpredictable. The tiniest perturbations of some of these other bodies out there would change things dramatically. And so people don't really know where it's going to be in the future, which is, it's far enough away from us. It should be cool. But it's quite interesting. So it actually takes like 250-ish years to go around the sun. And so we haven't actually seen it go around the sun entirely. Actually, this picture up here that you're looking at is a simulation. So we're going back from Pluto's, this is from 1850 to 2097 is what you're looking at. So it's a very long year out there on Pluto. What else can we say about it? It's rotating a bit slower too. Its turn, so its day length is about 7 Earth days. Well, 6.387, so closer to 6, I guess. But it's, on the order of a week. It also rotates on its side, sort of like Uranus, which is quite interesting. And of course, this is, has to be considered this is, I think, part of the reason that people are, in addition to it looking a lot like a moon of Uranus or something, it also seems to be orbiting in a way that suggests that it's maybe recently, on the solar system scale, recently left its orbit somewhere else and come into its own orbit around the sun, which is quite fascinating. I think, if we could see one of these moons become a planet in real time, that would be the biggest discovery in all of planetary sciences, but it might happen. So because of the fact that it's on its side and it has these really long seasonal extremes, it has these very extreme solstices too. So, at the solstice, a quarter of its surface is in continuous daylight, and the other fourth, another quarter of it, is in complete darkness. And, people are trying to understand why these things are tilted on their side. And the best guess about that is something called a true polar wander, which was a mechanism that was investigated in the early 20th century concerning our own ice ages, right? For why do we have these glaciers every, 26,000 years? And I think I mentioned this gentleman wrote a book that was very popular, Charles Hapgood, about the idea that the Earth itself, the crust may have slipped a little bit, and this might be a periodic fashion. And actually, Einstein wrote the foreword for that and did some calculations, and he was a big fan of the idea. He actually endorsed it. But, this idea fell out of favor, particularly with the advent of new plate tectonics ideas and so forth. But it does seem to be a reasonable candidate for the tilt of these big icy bodies. So the idea with true polar wander is that you have ice build up at some extreme, let's say at the polar caps, right? And eventually the thing gets a little unstable because it's heavier at these ends, right? And since a body that's spinning tends to relocate its mass at its equatorial axis, the idea is that these poles would just shift over time, right? too much material builds up here, and as it's spinning, it kind of turns on its side. And so this is the best explanation for why it's tilted sideways. And I'm not sure if people are applying this to Uranus so much, but it is interesting that the mechanism still, while no longer really being considered for Earth, it is certainly a mechanism that's being entertained for other bodies. Actually, I think that the most popular explanation for our own ice ages is this Milankovitch cycles, which has to do with the summation of different processes, slight changes in the tilt and eccentricity of the Earth over geological timescales, but it's far from zipped up. So, yeah, it's quite interesting. True polar wander. Now, Pluto was, it's another one of those heroes of predictive mathematical astronomy. Its location was essentially announced before it was discovered. So these astronomers were looking at Neptune's orbit in the late 19th century, and they had this, after Neptune, and they were looking at Uranus, they noticed Uranus's orbit was being slightly perturbed. It was being pulled out by somebody, and they called this planet X. And they went looking for it, and there was all sorts of commissions put together, trying to different astronomers getting together to try to get through to this. And actually, a young gentleman ended up getting the job. This gentleman named Clyde Tombaugh, who was 23 years old. And Tombaugh actually made a device where he was able to very quickly shift back and forth between views of these photographic plates so that he could see any minute movement of any objects that changed positions between the different photographs. And by doing this, he actually found Pluto, which is pretty cool. And so it was the first object discovered, so this was in 1930. It was the first object that was found in the Kuiper Belt, and very quickly celebrated as the 9th planet, which of course then fell out of favor as we found more and more of these things. So there's still a number of astronomers who consider Pluto a planet. It's rather, I don't know why people lose their minds about this so much. It's all a continuum, right? I hope you've learned that in this class, if nothing else, that all of these bodies are on a continuum. Even stars themselves are on the same continuum with a lot of these planets, right? Jupiter is it's compositionally very similar to a star. These brown dwarfs are essentially stars that failed to form. And so these delineations are useful in terms of being able to discuss things practically, but they're a bit artificial as well at the same time. Oh, there it is. I did have a picture of it. Nice. So you can see it next to our own moon. The surface of Pluto, similar to Triton, is about 98% nitrogen ice, traces of methane, carbon monoxide. And the mountains are almost entirely water ice, which is pretty cool. It's also one of the most contrastive bodies in the solar system, so it has a lot of dark and light regions. It sort of goes anywhere from this really deep night black to this dark orange and white. And the color's actually more similar to Io than it is to, say, Mars or something, although it's quite red here. Let's see what else we can say. Oh, the composition, yeah. So there, again, like some of our other moons, it's fiercely debated whether it has a subsurface ocean, which would be very cool. If we're going to explore beyond the solar system, we're going to have a nice waypoint at the edge, a nice gas station. And so there's hope that Pluto could be that body. People think that its internal structure is differentiated, much like the Earth. So it has some sort of a dense core and a mantle. Nothing generating magnetic field, so probably nothing molten at this point. But yeah, a lot of hope. People are really going back and forth on this as to whether there's any kind of subsurface ocean down there. If it was so, it'd probably be something like 100 kilometers deep, right there at the core mantle boundary. And if it's there, it may have been habitable in the past, and it's possible that those water mountains are the result of some sort of ice volcanoes that may have emerged in the past, but nobody knows for sure. Again, little tiny atmosphere on this thing, mostly nitrogen, methane, carbon monoxide, which are in some sort of evaporative equilibrium with the ice surfaces. Very, very weak pressure, about 1 pascal, right? So that's about 100,000 times less than our own atmospheric pressure. One thing that's really interesting is that Pluto, since it was first studied up close, measurements were returned about 2016. Since we've looked out, we had the opportunity to see it pass in front of a distant star. We were able to get some atmospheric readings, and we saw that actually the atmosphere had decreased by 20% in 3 years, which is pretty wild. Of course, this idea that these atmospheres are decreasing at an extraordinary rate on planets in general is a relatively new idea. And that, of course, didn't figure into most of our early solar system models. And I think that tells this story of the evolution of these bodies, from one stage to another, which is really fascinating. I mean, you got to think that the speed at which these new ideas are coming about is just completely unprecedented in science. It's very, none of us remember it, but as recently as the 1800s, Darwin was in the 1700s, crossed the border into the 19th century, but people generally believed that all of the different things on Earth started out there, right? So, the fish started out as fish, and the people started out as people. And this idea of evolution was very unpopular initially, and it was fought fiercely for, maybe close to 100 years. And I think that we're seeing a very accelerated version of that in planetary sciences, right? Where initially, as recently as when I was a kid, everything was formed. Everything started exactly as it was, where it was, and that's just become an increasingly untenable proposition. And so the evolution of these bodies, that they might start off looking like one and end up as another, is a really tantalizing, but it seems to be a very conserved feature of how we understand nature. And so look forward to more of that in the future. All right, well, Pluto, yeah, I guess I've already covered that. So, there was this early idea that Pluto was perhaps a leftover moon from Neptune. That's not as popular as it was originally, mainly because it seems like it's locked in this resonance such that it never really approaches Neptune in its orbit, and it's thought that it perhaps couldn't have in the past as well. So once people started finding all of these other bodies out there, people began to think that, okay, perhaps the origin of these bodies actually was something more like an agglomeration of comet-like bodies that happened way out in the outer belt, in the Kuiper belt. And so I think that's probably the most popular idea right now. It's thought that if Pluto was just plopped next to the sun, that it would look a lot like a comet. It would be shedding this big tail, and we're going to do comets next class. Hopefully, maybe they'll be pushed back to Monday. But a lot of these objects seem to have the same or very similar composition to comets in general, and so it's thought that they were actually captured up from the Kuiper belt. So, when the solar system was forming, there was all these little planetesimals, gazillions of them. Most of them suffered collision fates, or they were swallowed up by the sun, or they were destroyed into millions of pieces, like the asteroid belt. And so Pluto is thought to be one of these, something that formed out there and didn't fully coalesce. But Nobody really knows for sure, is the interesting point. Actually, the further we get away from the interior, the less we know. Pluto's had the privilege of being studied up close by this New Horizons probe, but the data is thin, and it's very, very difficult to see, even with our nice telescopes. All right. Pluto's got some moons. What's really interesting is that one of the larger moons, Charon, actually might be best considered, Pluto and Charon might best be considered a binary pair of dwarf planets, because actually they orbit a central point, right? It's not like Charon just orbits Pluto, as you would think of with like our Earth and Moon. In this case, the barycenter, it's a good word for you, where the center of their two masses were, if you were to just smear them out, is actually outside of Pluto itself. So that's quite interesting. And here's a picture of it. And you can see Pluto's kind of wobbling a bit there, right? Pluto at the center is also making a little bit of a circle as it's pulled around by Charon. What else can we say? So Charon's got it's thought, from some Earth-based observations that there's these patches of ammonia hydrates and water crystals, and so there might be active cryogeysers. We don't know for sure. Let's keep going here. Again, Charon's got this brownish cap, which is probably the same Tholin business, which again could represent something that's essential regarding life. We don't know yet. I'm going to spend too much time on Charon. I'd like to get to the asteroids. Nothing too surprising about its composition. Very similar to some sort of comet. People don't really know, actually. There's like this debate about which one is the case. Is it differentiated? Is it not? We don't know. I don't want to spend too much on these things we don't know, because they're less interesting. All right, let's get into the comets with the last 20 minutes. Comets. Let's get into the asteroids a bit, because asteroids are really important to us here on Earth. Before we do that, though, let's make sure that we understand the difference between these four classes of bodies, because they're always confused. So an asteroid is literally just any tiny planet, okay? Which is very strange. So asteroids, most of them are found within this belt between, we'll look at the belt in a second. Meteoroids, on the other hand, they're much smaller than asteroids, and we think that they're actually just fragments, right? There's some sort of collision impact debris that's floating around. They could be coming from the breakup of an asteroid. They could also be coming from something ejected from, say, a collision with the moon or with Mars. And so meteoroids are one step down from asteroids. Now, meteorite is something that's actually come through our atmosphere and hit the ground. So meteoroid, still out in space, meteorite on the ground. And then the final class are comets. And comets are different because they're icy. So as the sun warms them and they get hit with all of this solar wind, they outgas and they release these beautiful tails of, there's actually two tails on comets, one from the ionized material and one from the dust as they trail. And the ionized material, this gas that's being blown off, is actually always pointed away from the sun as it goes around. It makes its orbit. They make these really long elliptical orbits from the outer reaches of the solar system. Whereas the dust tail of comets actually kind of traces their path in their orbit. It's left behind them. Okay, so there's those four terms which we want to keep an eye on because they're very easy to confuse. Right, so here it is. A little bit bright. Oh. All right, so just so you can see it. So most of the asteroids are found in this big, broad space between Mars and Jupiter, and we call this the asteroid belt. And right now, we know of more than we've actually tracked more than 1 million of these things. And so what's interesting is that though there's so many of them, they actually only constitute about 3%, in total, about 3% the mass of our own moon. So they're very rarefied. And this is an interesting, we'll get to this in a minute, but you see these movies where people are going out into the asteroid belt and they're like driving their spaceships and like dodging the asteroids. And this is actually a bit preposterous because there's something like 100,000 kilometers between each one of these asteroids, right? So, we've sent probes straight through the asteroid belt, no problem whatsoever. Turn this back up a little bit. And almost all of these have really stable orbits, right? That's what we mean by belt. They're just out there in these slightly elliptical, but really solid, stable orbits. And they go around the sun about every 3 years, 3 to, I guess, anywhere as much as 6 years. But we're very interested in them, like I said, because of the possibility, some of these asteroids don't exist in the asteroid belt. There's quite a number of them that are actually in the interiors, and they constitute a pretty serious threat to everything we've got going on here on Earth. So there's a couple of favorites which are worth mentioning. I won't dwell too much on them, but we'll talk about Ceres predominantly, which looks a lot like a planet actually, and Vesta. So Vesta is interesting because it's very reflective. It's thought to be terrestrial, similar to Mars and Mercury, rocky and dense. Ceres, on the other hand, over here, it's ice and rock, right? And so it has this rigid crust, which is very much like pavement, and a less rigid interior. So it's flexible. Vesta, on the other hand, is interesting because it seems to be covered in basalt, much like our own mountain ranges out here, which indicates that it must have been volcanically active in the past, which is very strange because it's so tiny. It's only 300 miles across or something like this. So the story of Vesta is interesting. How do you get volcanism on such a tiny little thing, right? It doesn't have any of the differentiated processes that we would expect for that. Maybe it's a remnant, right? Maybe it's left over from something very, very old. We don't know. Now, Ceres was actually discovered a long time ago, which is quite interesting. And again, it's one of those triumphs of mathematical physics, which we love to trot out and talk about how smart we are. But it's actually it's a relatively simple calculation. So this gentleman named Johann Bode published this law. He actually stole it from this guy named Titius, and he was kind enough to share the name of the law with him, the Titius-Bode law. And basically what he did, actually, I'm going to just quote you his own words because he can explain it to you better than me. He was trying to find an explanation for the existence of a missing planet that he speculated to be out there, which turned out to be the asteroid belt. And he wrote, "The latter point seems in particular to follow from the astonishing relation which the known 6 planets observe in their distances from the sun. So let the distance from the sun to Saturn be taken as 100 arbitrarily. Then Mercury is separated by 4 such parts from the sun. Venus is 4 plus 3, which is 7. Earth is 4 plus 6, which is 10. Mars 4 plus 12, which is 16. Now comes a gap in this so orderly progression. After Mars, there follows a space of 4 plus 24, which is 28 parts, in which no planet has yet been seen. Can one believe that the founder of the universe had left this space empty? Certainly not. From here, we come to the distance of Jupiter, 4 plus 48 equals 52 parts, and finally to Saturn, 4 plus 96, which is 100 parts. So there was a gap, essentially, right? There was a very predictable gap where something should have been happening. And that is how people began to develop and start looking for these bodies. And so, let's see. A bit later, 1800, some astronomers, looks like they were in Germany, actually published the existence of several of these. They didn't see Ceres at first, but they found Pallas, 3 Juno, and 4 Vesta, which we talked about Vesta already. a bit later. It looks like in Italy, they found Ceres. It was a guy named Piazzi. And so this is kind of interesting. This is Piazzi's quote during his discovery of Ceres. He wrote, "The light was a little faint in the color of Jupiter, but similar to many others which generally are reckoned of the 8th magnitude. Therefore, I had no doubt of its being any other than a fixed star. The evening of the 3rd, my suspicion was converted into certainty, being assured that it was not a fixed star. Nevertheless, I made it known. I waited till the evening of the 4th, when I had the satisfaction to see it had moved at the same rate as on the preceding days." So it was not a fixed star, it was moving, and that was it. He then went on and made 24 more observations over the next year, it looks like, and then announced his discovery in 1801. Very cool. So the asteroid belt has about 75% of all the asteroids that we know of, which I said are well over 1 million at this point. But again, the average distance between these things, even in the belt, is about 100,000, I said kilometers, 100,000 miles, actually. And there's probably lots of little debris in there too, but when we sent our probes through there, especially Voyager 1 and 2, they had no problem. Nobody was getting decked by asteroids, like you would see in Star Wars or something. And of course, this worked out for all the other spacecraft like Galileo and Cassini and New Horizons, which went through without a problem. So when it comes to asteroids, there's a number of classification schemes, and these are all falling apart, which is a bit of trouble. People can't really decide how to classify them. They group them into families based on how they orbit. Some of them orbit with high eccentricity, and some of the classification schemes have to do with their composition. So your textbook seems to fixate on the composition, which I think is wise, primarily because it helps, it's a shared compositional structure that we look at with meteors, and they can also teach us a bit about the early material in the solar system, and so we'll mainly talk about those. And so you essentially have the C-type, the S-type, and the M-type, right? So you have, and the M-type is also thrown into this, it's sometimes called the X-type, but they're basically metallic bodies. The C-type are very carbonaceous, they're black. The silicate ones, S-type, are rocky, and then, of course, the metal ones, which are iron and nickel. Let's see. Most of the asteroids we see are dark, are of the dark kind, this carbonaceous. But there's a few of the others. Let's see here. What about where do they come from, the asteroid belt, you know? This has been another one of those debates that continues up to the present. It's thought that I think that the most popular theory right now is that they're busted up planetesimals from the early days of the solar system. There's been a number of arguments over the years that it's the result of some planet that got smashed up, but none of these have really held sway so much as people are thinking that they're actually, and this is because they're all very different too, right? So the fact that you have carbonaceous ones and silicate ones and rocky ones, people think that they must have formed, there must be individual planetesimals, ones that were rockier, ones that were more metallic, and then they blew into pieces, which is interesting. I mean, it occurs to me that if you took a differentiated planet like the Earth and you smashed it to smithereens, that you would probably end up with pieces of it that were metallic and pieces of it that were silicate and so forth. So I'm not sure why that's completely been dismissed, but there you have it. So let's see, how much time have we? About 10 minutes. Let's talk about asteroid mining. You know, one of the big reasons for doing asteroid mining is that it would actually clean up our environment here on Earth. And that's been kind of used as the motivator for why we should be out there. If we could, of course, stop digging up using child slaves in Africa to dig the rare metals that we need for our iPhones out of the Earth, maybe it could be done in outer space robotically, and it would be a much better humanitarian and environmental situation. But there's some problems with that. So it's like right now, I think the most material we've ever brought back from an asteroid, actually I'll have the figures from this. Maybe I have them here. Yeah, okay, so this is interesting. There was a probe called the Hayabusa, which I believe was a Japanese probe. It brought back, let's see, a gram of material. That cost $300 million. The second one, they're planning another mission, which is hopefully going to bring back 60 grams, $800 million. So the idea of being able to bring back appreciable amounts of this material is a bit out of reach right now, and I think that's why companies have scaled back their interest in it. And like I said at the beginning of class, almost all of these companies, there was a big boom, almost like the dot-com boom or something. Everybody started an asteroid mining company back in the 2010s, and almost every single one of those companies has converted or been bought up or agglomerated into some sort of a propulsion technology firm at the moment. Because people have their eyes on getting to the moon and setting up base over there instead. So how do we do it? One idea is we bring the stuff back to Earth. That's very expensive. Another idea is that we process it right there on site, make our own propellant for the return trip there, and then send it back robotically. You could also transfer it to a safe orbit, say around the moon, and do all of your industrial processing there, which could allow for a lot of the materials to be used and not wasted. Each one of those asteroid types has a particular benefit. So the C-type asteroids have a bunch of water, which it could be used for the mining itself. It could also be used for propellant. They also have a great amount of phosphorus and carbon, which could be used for fertilizer. If we do end up terraforming, say, parts of the moon, or we have greenhouses set up, we do terraform parts of Mars, we're going to need lots of fertilizer. It's actually one of the biggest challenges in terms of exploring Mars right now. How do you get fertilizer out there? So perhaps we can make it. The S-type asteroids, they don't have much water, but they're attractive because they have a bunch of other metals as well. So they have some nickel, cobalt, and some really valuable ones that the humans love to death, like gold and platinum and rhodium. It seems like a typical S-type asteroid, it's like 10 meters in size, might contain as much as 1.5 million pounds of metal with, maybe 100 pounds of these really tasty metals like platinum and gold. And then the M-type asteroids, like I said at the beginning, they're extremely rare, but they probably have way more, maybe 10 times more metal than the S's. And people are starting to narrow down the database of ones that we could actually get to. And we call these easily retrievable objects. And these are, I guess they have about 12 of those that they have their sights on. The thing that they like about these is that you could easily change their velocity a little bit and kind of steer them. This is very, very, very scary. Steer them over towards Earth. Yeah? At which point we could get to them easier. Of course, there's a whole other team of scientists at the other end of the building who are like, how do we steer the asteroids away from Earth? So we'll talk about those. I think we'll probably have to do those, the Earth defense next time. So it was calculated back in the 90s, late 90s, around the turn of the millennium, that a typical asteroid would contain almost $20 trillion worth of industrial and precious materials. Wow. So this is a huge cash cow. It's very attractive industrially. And actually, we can thank Elon for developing these Falcon Heavy rockets because they've lowered the cost of getting things up there. It seems like in terms of getting access to these near-Earth asteroids, the cost since SpaceX has been up there of actually getting a rocket up into space has it has actually, how is the best way of putting this, is increased the number of accessible asteroids to us of the total asteroid pool from something like 3% to 45% of the asteroids. So it's increasingly possible, but I think that no one is really fixated on it until we get some serious moon bases set up, and that's of course happening. We've had some discussions in this class earlier, like just because we can do it, should we do it, right? And one of the biggest problems with this, and I think it's going to have to be solved eventually, but we're nowhere near close to solving it, is that spending a lot of time in space really messes you up. It's really, really bad for humans to be out in space, it turns out. Parker always has these horrified looks on her face when I talk about the humans being industrial in space. I understand. So it has devastating impacts on people's psychology. It changes our brain structure, our neural interconnectivity. The cosmic radiation's terrible on our brains. They've taken some mice up into space, and they have problems with memory. Their neurons stop being connected to one another. Their memory, I said memory already. And they also, all of the animals reported an increase in fear and anxiety. There was a really, really cool experiment that was done on Earth. Maybe I'll just stop with this little story, but it was called the Biosphere 2 experiment. And I actually had a chance to sit down with one of the guys who was in this experiment, but they locked a bunch of people, and they made this. It's actually a really, really crazy, cool story. So this is really this group of this theater troupe back in the 60s or 70s. They built. They were, eco-radicalists, right? They were all hell-bent on saving the Earth and so forth, like so many people were back then. And they built this sailboat, and they were traveling around the world, and they were doing theater and all of this stuff. And they got this idea that, hey, what if we do an experiment where, or it was actually more, it was envisioned as like actually a piece of theater originally. What if we lock ourselves in a box for, I think they imagined doing it for many years originally. They ended up doing it, I think, for 2 years. Things went sideways. And what if we were able to show that we could create a sustainable Earth if we were cut off from the outside world and we didn't have all of these industrial pollution and all of these things, and we could live harmoniously? And there's a couple of I really recommend that you guys check out some of these. Just go and Google Biosphere 2. There's a really good documentary about it. They got a ton of money from some billionaires, and they built this thing out in the desert. I believe I want to say it was in Arizona. It may have been New Mexico or Nevada. I can't tell the three places apart very well. But out in the desert, they built these domes. And almost everything went wrong that you could imagine going wrong. They learned a ton, but one of the most troubling aspects of the experiment was that the people started to not get along with one another, right? They were locked in a box for like 2 years together. The food sources, they tried to farm their own food in there. Of course, people started losing weight. At some point, their CO2 scrubbers started failing. They were getting kind of lethargic and deprived of oxygen. People started stealing food. People started hoarding food. It was a really nasty situation. And so anyways, going to set up these bases is going to require rethinking not only the technology of how we sustain life out there, but how we get along with one another, which I think is something that we're very concerned about here on Earth right now as well. All right, let's stop there, and we'll pick up with saving our Earth from asteroids next time. Have a great week, guys.